Hello guys, this is Baek Kim. Today I'm going to explain about quantum cascade laser. So do you know why the name is laser? The funny thing is that the name was first loser, which stands for light oscillation by stimulated emission of radiation. This is a disaster, right? So scientists changed the name to laser, which stands for light amplification by stimulated emission of radiation. But scientists was not happy because it sounded like lazier. So anyway, we have to know what stimulation means. So what is stimulation? Is it like acupuncture? It hurts, right? And it stimulates your body. Same thing happens in the stimulated emission. Think about two energy level, which is ground and excited levels. If photon energy comes in, which has large energy, then the electrons in ground level jump to the excited level. If we just let the electron at the excited level, then it will spontaneously fall towards the ground level. Here the phases are random. Suppose you have a lot of electrons in the excited state. Then what will happen? Because we give external stimulation to the electrons, it will fall down to the ground state. Photons come out and their phases are same, which gives constructive amplification. When the number of electrons in the excited state exceed that of the ground level, we say this population inversion. So this is the first condition for laser amplification. Now you know the stimulated emission is something like this cartoon. And now you know you need lots of electrons in excited state for stimulated emission. Oh, but wait. What if electrons fall down as soon as they jump up? Hey, stay there! Oh, we cannot because of the Boltzmann statistics. No population inversion, then no laser. We need a little trick to avoid this. Then how can we solve this? Let's look at this three-level system. Once electrons jumps up to E3, it quickly falls down to E2 and stay there. But why? Because E2 to E1 transition is very slow. In this process, the electrons at the E2 level will get accumulated as time goes. So we can get the population inversion, but there's a problem. How can we amplify our in-phase photons without losing them? We need another trick for this. So look at this picture. Photons are moving back and forth between these two mirrors. We call this device resonator. LAMP skips photons for optical pumping and leads to the population inversion, generating in-phase photons. And they are again while they move back and forth. Finally, laser comes out from the half mirror when enough photon energies are stored. Scientists thought about the semiconductor version of laser. Yes, actually they are busy people, not lazier people. They used pin diode, so that we call it laser diode. N. Hall and M. Nathan from the different organizations have observed the coherent light emission from the diode. Let's see what happens in pin laser diode on the forward bias. So here, electrons flows into intrinsic region, and the holes flows into intrinsic region on the forward bias. They recombine and generate photons. We say this interband transition. But the place where electrons and holes meet is too narrow. But what if we use narrow bandgap material for I layer? Then we can stop electrons and holes flow out because it is trapped. Then we can make electrons and holes recombine efficiently. This is called heterostructure laser diode. But as we discussed previously, we again need an amplification to make a laser. So we need a resonator again. But the good thing is, when you break a crystal along crystallographic direction, flat mirror automatically forms as gems do. We call it cleavage plane. So resonator forms by itself. Okay, from now on, we are going to make infrared laser diode using pin diode. Then why suddenly infrared? As you know, infrared light is the light with long wavelength, and this property is quite useful. For example, the infrared goes deeper, so we can use in biomedical region, and the infrared also goes far, so we can use at remote sensing. Then how to make it? It's easy. Just reduce the band gap. But there is some problem. When the wavelength is 5 micrometer, then the band gap is only 0.3 electron volt. Then too much thermal noises happen. Electrons jump up and down like a crazy guy by thermal energy. Then how can we solve this? Should we just put this guy into a liquid nitrogen pool? Because we can cool it, right? But it's a totally bad idea. So we invited a new guest, Professor Capasso. Professor Capasso, please help me. Okay, now we focus on the conduction band. And now we stack AB quantum structures. Here, A is quantum well and B is tunneling barrier, but the barrier is very thin enough to allow quantum tunneling. This shape looks like Cascade, right? In here, for the transition, E1 and E2 levels should match. We say this resonant tunneling. In here, when electrons fall from E2 to E1, then infrared photon comes out. We say this inter-subband transition. Is it all done? Wait, but it is not a laser. Can you guess why it isn't? Yes, it's because there's no population inversion. Then can you remember what we did previously to get population inversion? Yes, it's the 3-level system. We need 3 levels to delay the transition. There exists 2 layers. First, the active layer consists of 3 quantum wells. Quantum well 1 is very thin, and quantum well 2 is wider, and quantum well 3 is a little bit wider than quantum well 2. Quantum well 1 is so thin that the ground energy level, which is E3, matches to EC. Now electrons tunnels in E3 level, and electron has no way to go except to E2. The transition is delayed because 2 levels, E3 and E2, are spatially separated and energy difference is large. So now we can have population inversion. When electron falls down to E2, it moves to E1 and then quickly tunnels out. And now, what we are going to do is, we are going to connect these quantum cascades. Then, electron which enters in injection layer should lose its energy by scattering to fall down to the next well's EC. Then what do you think about the emitted number of photons? It would continuously amplify if you keep connecting this thing, right? Actually, Capasso reported that he connected 25 amounts of quantum cascades. Then it can amplify the photons more and more, about 25 times. It is really challenging. So where are they used? It is used at gas sensing because gases absorb infrared light, or real-time monitoring of air pollutants or airborne particles, and etc. These are the references. Thank you for watching my video, and have a nice day.